Alright, so we're going to do some problems dealing with the work energy theorem and a couple of example problems and see how this idea can be applied to some other types of problems. So here we have a skier, mass is 75 kilograms, going down a slope that's angled at 20 degrees from the horizontal in the picture shown below. Distance down the slope is 50 meters. There's no friction acting on the skier. If the skier stops at rest, how fast are they moving at the bottom of the slope? So let's collect some information. There's one piece of information. It's 50 meters down the slope for the skier. We know that the weight of the skier is acting downward. We know that there's some normal force which acts up, well, perpendicular to the slope. We know that the weight is perpendicular to the horizontal. And so the weight and the distance traveled have to be 70 degrees apart from one another. So that's important because basically what I've done is I've drawn a free body diagram in here, and I've decided what direction the skier is going to move, and I know that it's a 70-degree angle here and a 90-degree angle between the distance and the normal force. So if I can find the network, I can find the change in kinetic energy. Since the person started at rest, their kinetic energy initially was 0, so I could find the final velocity. So the network on this skier is going to be the work done by gravity, what I'm going to call Wg, and the work done by the normal force, and I'm going to call Wn. So if I plug in the pieces of information I know, Wg is going to be the weight, mg, times x, distance, times the cosine of the angle between them, 70 degrees. For the normal force, it's going to be whatever the normal force is, times x, times the cosine of 90 degrees. Now I could work this out and figure out what the normal force is. It's something I could figure out in this problem. But ultimately, since the cosine of 90 degrees is 0, the normal force does no work. So really the net work is just the weight times the displacement times the angle between the direction down the ramp and the vertical, 70 degrees. So this means the change in kinetic energy is also mgx cosine of 70 degrees. That's where the work energy theorem comes in, that work is equal to change in kinetic energy. So 1/2 mv final squared is equal to g times x times cosine of 70 degrees. I don't remember whether I gave you the mass of the skier or not, but what it looks like is that mass cancels out. So whether I gave you the mass of the skier or not is really not relevant. And so really v final squared is equal to 2gx times cosine of 70, where this 2 came from as I multiplied by 2 on both sides. Square root both sides and you find the skier is moving 18.3 meters per second down the slope at the bottom of the slope. Now the thing to point out about this situation is that this is mass independent. It doesn't matter whether it was me or 3 of me or the smallest person you can imagine. 18.3 meters per second is the speed that the skier is moving at the bottom of the slope. Now let's make this a little bit more realistic of a problem, and let's add friction to the equation. Same exact slope, same exact skier, same exact distance, except where there's a constant frictional force of 100 newtons acting on the skier the entire way down the hill. And I want to figure out how fast the skier is moving at the bottom of the slope. So we can start off the same way. I've got a displacement of 50 meters. I've got weight, friction, and normal force are the 3 forces acting on the skier. So there's my free body diagram for the skier. I know that weight, again, is acting at a 70-degree angle from the direction of travel. It looks like frictional force is 180 degrees, opposite direction of the direction of travel, and normal force is still perpendicular. So again, if I find net work, I can find change in kinetic energy. The only term I'm adding here is work due to friction. So this is the exact same problem, except I've added friction to the equation. So when I add out my work terms, I now have weight times displacement cosine of 70 degrees. Frictional force times displacement times cosine of 180, because that angle there is 180 degrees. Normal force times displacement times cosine of 90. Normal force cancels out because cosine of 90 is 0. The cosine of 180 is -1, so I could rewrite fx cosine of 180 as just negative fx. So this means the network is equal to mgx times cosine of 70, the work done by the weight as the skier goes down the ramp, minus f times x, the frictional force times x. Again, by work energy theorem, that's equal to change in kinetic energy. So 1/2 mv squared is equal to mgx cosine of 70 minus fx. So let's do some algebra to solve that. Looks like multiply everything by 2, divide everything by m. So the m cancels out here. Here we get 2 divided by m. And then I take the square root of everything. And so if I plug in my numbers, the skier's speed is now 14.2 meters per second which is less than what it was before. The one thing to point out is that this is mass dependent. Larger massive objects, if I was heavier or have a larger mass, this term gets smaller because I'm dividing that work due to frictional force by a smaller mass. So the larger this mass becomes, the closer and closer it becomes to a frictionless system. The friction is small in comparison to the weight of the object. So let's assume we wanted to find the coefficient of friction instead of final velocity. Since the skier is going to be moving with respect to the slope, this is coefficient of kinetic friction. We'll assume we didn't know the frictional force, but we knew what the skier's starting velocity was at rest, and we knew the final velocity was this 14.2 meters per second. So let's kind of work this out. So what I would now know is what the final kinetic energy is. I would also still know this because I know it's a 75 kilogram skier. So what I'm going to do instead of having Fx is I'm going to substitute normal or coefficient of friction times normal force in for frictional force. So get this equation. And here is the thing I'm looking for right here, coefficient of kinetic friction. So I need to figure out the normal force first. The way to do this is to say sum of forces in the y direction, so in this direction is equal to 0. So normal force times the y component of weight is equal to 0. The y component of weight is mg cosine of 20. So normal force minus mg cosine of 20 is equal to 0. So normal force and mg cosine of 20 are the same. So I can take it, substitute that in for normal force, and there we go. Looks like at this point I'm going to divide the m out. There's an m in every term. And get 1/2 v final squared gx cosine of 70. Coefficient of friction times really gx cosine of 20. From here I could subtract gx cosine of 70 to get the coefficient of friction by itself on the right hand side. I then divided everything by negative g cosine of 20 x, and then plugged all my numbers in and got the coefficient of kinetic friction as 0.145. So I could use this work energy theorem in other ways to calculate something like the coefficient of kinetic friction, something that doesn't seem like I should be able to do it right away. So those are 3 example problems that I use the work energy theorem to solve. The first one a relatively straightforward one, the next one a little bit more complicated one, and this last one I think is a fairly challenging one on a scale of 1 to 10, probably a 7.5, 8 difficulty problem. The thing to point out is that there are a variety of different types of problems you can use work energy theorem to solve. Some of them look like problems that we would solve before using Newton's laws. In fact, all of these problems we could have used Newton's laws and kinematics to solve. This is just an alternate way to do that type of problem. Instead of doing it in 2 steps, we're doing it in 1 step. So the next lesson we'll look specifically at work done by gravity, because there's some interesting things that happen with a force like gravity that we can use to make a problem like, well, this problem actually a little bit easier when we work it out using what we call gravitational potential energy.